Hello everyone, let's try to be a cheat code ninja today. In this problem, we have to implement a queue using only two stacks, and the queue must support the following operation. We must be able to push an element to the back of the queue. We must support the pop operation, which removes the element from the front of the queue and then returns it. Our front element is 1, hence we'll remove it. We must support the peek operation, which returns the element at the front of the queue without removing it. So in this case, the element at the front is 2. And finally, we have to support an empty operation, which checks if the queue is empty or not. Let's look at the example given. Initially, we are creating an empty queue. Now we'll push 1 to the back of the queue. Similarly, we'll push 2 to the back of the queue. Now we'll perform a peek operation, which returns the element at the front without removing it. Hence we'll return 1. Now we'll pop the element at the front of the queue and then return it. So we'll remove 1 and then return it. And in our last operation, we are checking if the queue is empty or not. We still have one element in the queue, hence the output is false. Let's go through the properties of a queue and a stack to come up with our solution. A queue by definition works on the principle of first in, first out. So elements are added to the back and then removed from the front. For example, we are adding 1, 2 and 3 to the queue. This order will be maintained when removing the elements from the queue. So 1 will be removed first and then 2 will be removed and then 3. The peek operation will return the element at the front of the queue. We have removed 1 and 2, so now 3 is the front of the queue. And now when we try to add another element 4, it will go at the back of the queue. A stack by definition works on the principle of last in, first out. So the elements are both added and removed from the back of the stack. For example, if we add the elements 1, 2, 3 to the stack, they will be removed in the reverse order. And if we now try to add more elements, our stack would look like this. In both these cases, we are adding elements to the back of the data structure that we are using. So a push operation can easily be maintained by a stack. And for checking if our queue is empty or not, we can just check if our stack is empty or not. The problem comes when we look at these two operations, pop and peek. These operations work on the elements at the front of the queue, while on a stack we get the elements at the back very efficiently. For example, the pop operation should remove the element 1, but the top of our stack points to 2. Similarly, the peek operation should return the element 1, but the top of our stack points to 2, which is wrong. What we ideally want is the first element of the stack, and if somehow we could change the order of this stack so that the first element comes at the last, we could retrieve it very efficiently. So we should try to find a way to reverse the order of the stack so that the first element comes at the last. Luckily for us, we are given an extra stack that we can use. And for each element in our first stack, we could pop it and then simultaneously add it to the second stack. This will reverse the order of our original stack. Now for the peek operation, we could look at the top of the second stack. Similarly, when we pop from the queue, the correct element will be popped from the second stack as well. And a new front of the queue will also point to the correct element. Now let's look at the case when we push an element to the queue. Now we have two options, whether to add it to the first stack or the second stack. If we add it to the second stack, then it will become the new top of this stack, and when we do a peek operation, this element will be returned. But in our queue, the front element is different. Hence for a push operation, we cannot add elements to the second stack. Now if we add this element to the first stack, in this case, for the front of the queue, we can still refer to the top of the second stack. And similarly, when we try to push more elements, we should always push it to the first stack. Now let's try to do a pop operation on a queue. The first element to be popped is 1 and it will be popped from the stack as well. Similarly, we'll pop 2. Now this is the front of the queue and hence this should be popped. But in this case, our second stack is empty. So what we can do is remove all the elements from the first stack while simultaneously adding it to the second stack. So now we can safely remove the top of our second stack. Similarly, for our next pop operation, we could remove 4 in both the queue and also the second stack. So for both our peek and pop operation, if our second stack is non-empty, we can directly use the top element of it. Otherwise, we have to remove all the elements from the first stack and transfer it to the second stack. For checking if the queue is empty, we should now be looking at both these stacks, and if both of them are empty, then our queue is empty. For the push operation, we are directly pushing the element to the first stack, and this operation will take constant time. Similarly, for checking if the queue is empty, we'll check if both the stacks are empty. This will also be a constant time operation. For both our pop and peek operation, we are referring to the second stack. If this stack has element, then we can perform both these operations in constant time. But in the worst case, when it is empty, we have to transfer all the elements from the first stack to the second stack. For example, if these are the 5 elements in our first stack, we have to perform 5 pop operations from our first stack as well as 5 push operations on our second stack. This may seem to be a O of n operation for transferring n elements from the first to the second stack. But if you notice carefully, for the subsequent 5 next pop operation, we can use the results of a previous computation and perform the pop operation in constant time. And for our subsequent peek operations, we can use this pre-computed stack to return in constant time. So averagely, across multiple pop and peek operations, this can be achieved in constant time. And the space complexity would be O of n because we are maintaining 2 stacks. Let's implement our solution. To solve this, we need 2 stacks, so let's initialize them. For our push operation, we can directly push to the first stack. Let's implement the peek operation first. In this case, we have to handle 2 cases. If our second stack is empty, then in that case, we have to pop all the elements from the first stack and simultaneously add it to the second stack. After this, we can be sure that our second stack will never be empty, so we can directly return its last element. Our pop operation is also very similar to a peek operation. We have to make sure that our second stack is not empty. To ensure that, we'll just call the peek operation, and once we are certain that the second stack has elements, we can pop its last element and return it directly. And our queue is going to be empty when both the stacks are empty. So we'll check if both the stacks are empty, then we'll return true. We are done with our solution. Let's submit it. As you can see, our solution is accepted. If this video was helpful, please leave a like and subscribe to the channel for more such content. Thanks for watching.